Alright, are we live? Hello, 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 hello. Hola. Alright, so we have another problem today. Flatten a multi-level doubly linked list. We'll get right into that. See how this goes. I always like to take a few seconds beforehand and just take a moment, I suppose. Yeah, alright, let's get it going. Let's get it going and see how this goes. Good. You are given a doubly linked list, which, in addition to the next and previous pointers, could have a child pointer, which may or may not point to a separate doubly linked list. These child lists may have one or more children of their own, and so on, to produce a multi-level data structure as shown in the example below. Flatten the list so that all the nodes appear in a single level doubly linked list. You are given the head of the first level of the list. Head, output, multi-level linked list, and the input is as follows. Oh. Wow. Flattening the multi-level linked list to be look at this picture. Nice. Okay. Excuse me. 1, 2, null 3. 1, 2, null 3. How multi-level linked list is represented in the test case. Yeah, this is a little confusing. Won't have more than 1,000 nodes. Okay. Interesting. Addition to the next and previous pointers, it could have a child pointer, which may or may not point to a separate list. Child lists may have one or more children of their own, and so on, to produce a multi-level data structure. This is really weird. Excuse me. It's kind of recursive. It makes me think of like a tree, but it's not really a tree. It's like, I don't know. It makes me think of a tree that has horizontal siblings, I guess, but like the siblings are all connected. Something like that. I don't know. This is a weird kind of a data structure. I don't really know how exactly you're supposed to flatten this though, because each child could just be like the same data structure again, right? It's not really clear. Not really clear where that's supposed to go in the output, I guess. It's not just an array that we're looking for. We're looking for actually doubly linked lists. It's really interesting, but or interesting, but this 1, 2, null 3. What is this? How do we know the child for 1 is 3? Like, how do we know that? One, 3, 2. Also, why is it that this is how it flattens? I guess you process the child before you process the next node in the list. So you flatten recursively. Interesting. Representing the test case. Example 1. Okay, we go to 6, and somehow null, 7. Oh, I guess it's 1, 2, 3. That's how far. That's where the child is for 7. And then 8, 9, 10, null, null. So then it's got to be the second one. 8 is the next child. But you could have. But how would you input like another? You have another child here on 10, right? 10 could have 13, 14, 15. And how would that? How would you put that into? Excuse me, I don't think you can. I think it would not work. Serialization of each level is as follows. To serialize all levels together, we will add nulls at each level to signify no node connects the upper node of the previous level. Oh, I think I understand. The serialization becomes this. Merging the serialization of each level and removing trailing nulls, we obtain. Okay, I think I get it. Gotcha. Huh. Okay. Interesting. Well, we don't have to worry about that, the input too much. Because I'm probably not, oh, well, I should say that. I mean, we'd want to test a few different cases, I guess. Excuse me. So, I'm tempted to write this like completely recursively. I think it's going to be hard to do it totally recursively. I think I usually have like a recursive helper function. It's a little easier to work with. Also, if I don't need to include everything, well, this shouldn't matter. All right. Now, I don't know if this is just going to return null or what we're going to do here. So, oh boy, man, wow. Okay. Oh, my body is quite sore. Quite warm, I'm tired, sleepy, and sore. And my back and neck kind of aches. What are we going to do here? I don't know. I think the idea is going to be to flatten what the child is pointing to, if there is a child, and then link, you want the head and the tail of the so I'll have a pair, a return, and we're going to get the head node and the tail node of the linked list. And then we're going to make, we're going to attach the head to 3, right? So to the right of 3 will be the head. Point those to each other properly. Excuse me, and then the tail, the next node on 3 will have the tail point to 4 correctly. I think we just do it that way. So try to do it this way. And edge case. Now, I don't know if I can return a null pointer with a pair. I don't know what happens when we do this. Doesn't compile, okay. think we need something like this. Oh, it compiles. Interesting. Huh. Interesting. Okay. Yes, that's an edge case. By the way, I think we always just return the head. Because the head is always, if the child gets flattened and gets put to the right of the head, then the head is always going to be at the beginning, no matter what. If there's a child, there's no child, it's going to be at the beginning. If there is a child, it'll be at the beginning, so in either case, it's at the beginning. Okay, so it's actually, there really won't be an edge case, I think, where it's empty. So we'll say if we want to flatten each, so yeah, okay, I think I know what to do. So say current equals R. I'll do a for loop. Or we'll do, yeah, we'll do current equals R, and we'll say current child is a null pointer. And then we're going to update current to the next. Okay. Until the child is not a null pointer, we're going to scroll, and we'll say if, so if, we have another one too, while current, so while current exists and there's no child, we're going to keep scrolling until either we don't exist anymore or there's a child in the process. So if current and current child, then recurse f with f on current child. So we're going to get we're going to flatten the child data structure. And we're going to say standard pair or auto p. And we're going to say, we'll say head equals p first, tail equals p second, and then we're going to attach the head and tail of the flattened list. Appropriately. So this current next is now going to point to head. Head previous is going to point to, we're going to say, yeah, it's fine, actually. Just point to current. The tail next is going to point to temp next. And the tail next is going to point to temp next. And temp next previous is going to point to tail. Alright, so we get these links, these doubly linked links set up properly. And you actually want this in a larger while loop. put this in a double loop. Scroll to the next has a child. And so if we're not at the end of the list and we have a child, we're going to collapse that child and set up current properly. And then actually we keep going. Right, this is going to happen every time. So scroll again. Current child is a null pointer. Keep scrolling. Eventually we'll get off the edge. And then we're in pretty good shape after that. Excuse me. So this is the head. Yeah. So node ret head is going to be R. And we have a previous, it's going to be the tail. Actually also points to R. And we say previous equals current. And current next, same deal here, previous equals current. And we're going to say turn, can I do this? Ret head, previous. Something like this. And actually, I think this works if you do it this way. If it compiles. Also appreciate, oops, whoa. Didn't want to show that, I'm sorry. That is not information about myself I'd like to share with the world. Ugh. Sorry, we'll keep going with the video. How did that happen? Ugh. Gotta make sure I don't know how that happened. That was bizarre. Because that was not the last web page that I'd visited. I don't know what combination I did to reach that, but yeah, it's not information I want to share with the world. No, thank you. It's funny though that I missed like defining what these variables are. Pair. Are these pairs or yeah, it's a pair, right? Not a tuple. Non-const L value reference to type pair cannot bind to a temporary of type pair. Not what? Interesting. Good runtime error, but I wasn't expecting this to matter either. I was sort of under the impression that this would be fine to. I mean, I think this will use copy elision anyway. Like I think you could do like standard move to get this set up correctly. Not standard move, but I think this will do what we want anyway. I don't think we actually need the reference there, but something about it's kind of interesting, I suppose. Anyway, so what is this runtime error? Oh, yeah. But how come we actually need to check that? Because it's already here, right? Current exists here. So how is it possible? Oh, yeah, that's how you exit this loop. Duh, of course. Right. That makes sense. Scrolling within this loop. Okay, this doesn't make sense though. How does that cause an issue? What? How could it not be? Now that doesn't make sense though. Null pointer type node. No. Because clearly there's a check whether or not this is null. No. Right here. Let's check if it's null or not. How is that even possible? What is going on here? Test once. What is happening here? Hello? I don't actually really care about the value, but I guess it matters for. So 1711. Oh, okay. Oh, I see. So there was some recursion that was called. I have this child. I guess you get down to 11, and then what? Current's point to 11, previous equals 11, current equals 12, current's 12, 12, and it has a child, which is the null pointer, which is true, set previous to 12, current goes forward to it goes forward to the end. So current's at the end. Current at child. None of that matters. So this is empty here. And now this should be empty. This should just say. Oh, I see the problem. That's very subtle. That is extremely subtle. No kidding. Whoa. Oh man. Whoa. Whoa, 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 whoa. Right. So you actually don't need. You shouldn't even have this. This should be just a while loop. Actually, that's my mistake. I think I see the problem now. Yeah. Tealy. Okay. No, but that's not correct. That should Tealy. In this case, you would, after processing all of this, you would set, you don't set current to current next, you skip past newly constructed, flattened, and inserted list. Yeah, so this is going to be temp next. Okay. Something like this. Okay. 4 milliseconds. And it's wrong. It's close, but it's wrong. Okay. It's not a valid doubly linked list. Okay, it's very close. Now the question is, why is it not valid? Oh, we need to clear the child. Set the child node to empty. Right? There we go. Sweet. That took forever. That took a while. I don't know how long that took. 20, 30 minutes? Alright, we should probably try some other test cases. Alright, that's example 1. We have example 2. And 3. Think if it's not right. Would fail in these two cases. I think these are relatively complicated cases. Excuse me, I'm wondering if we can come up with one that has... I'll just go for it. I don't know. I'm trying to think of a test case. Oh. I was trying to think of a test... No, that's upsetting. I'm trying to think of a test case that, like how to construct a test case that has like multiple children at one level. Yeah, I feel like probably not going to get this one. I think problems with the test cases are kind of hard to put together. It's really awkward. I don't really hold myself to, I guess, I don't hold myself too responsible for this one because like it's kind of a pain in the neck to set up these test cases. Although this is interesting. I mean, I guess maybe I should have been able to think this through. Yeah. Alrighty, where's this runtime happening? Temp next, previous. Oh, I didn't think about that. If temp next is empty, it could be empty. Yeah, I don't really consider that. Current's not empty, but temp next could be empty. Yeah, so if you have a child but no next neighbor, didn't really consider that. Wrong. Nice. Interesting. So actually, that gets kind of complicated, doesn't it? Because you want the temp next could be empty. In which case, this is a little confusing. So the whole point is that you have this child node that you flatten, child structure that you flatten, and you hook up you kind of stitch that into these two nodes that you have linked to each other. And what I was suggesting was basically, well, if there is no node to stitch in, then you don't really need to do anything, I guess. Kind of just skip this part, pointing this node backwards. But actually, I do have a problem because this flattened structure, the base case, doesn't necessarily work out, which is what we have here. The problem we have here, where 2 should be stitched to 3. Actually, what's the issue here? Why is this not giving me... I actually don't think this should matter that much. So this one's just empty. Recursively flatten. Let's say we get that. We get 2, 3. 2, 3. Next is 2. 2 points back to 1. Tail is 3. That points to empty. And then the empty node doesn't point to anything. But what actually happens when you recurse, so temp next is empty, and we recurse on 2, which is sort of the same thing. You have 2 and then 3. So we recurse on 2, and then 2 ends up recursing on 3. We look at 3, there is no, the child is a null pointer. So we set previous to current, current to next. Current's empty. So we just return head and previous, which is 3. Right. So this is just 3 and 3. It's the head and the tail. And then we say head is 3, tail is 3. Current next equals head, so current at this point is 2. 2 then points to 3. 3 points back to 2. 3 points to empty node, and this empty node doesn't. Yeah. Wait, what's wrong here? And then and then current. That's why. I think that's why. Because now you update your empty here. Current red head is 2. Previous is. I think the previous doesn't get set properly, right? The previous before 2 is only a 1. I think that's why. The previous should actually be 3. Is that right? Is that the issue? Yeah, that's probably the issue. Should be the tail. Is that what we need to do? Yeah. That's really subtle. It's probably something else that I missed too. I'm wondering if I should try some other test cases. Yeah, probably. I don't know. It's kind of just unsatisfying now. I tried just kind of ran the test cases anyway. I'm just gonna do like 30 nodes. And then we're going to try the whole boatload of null values just kind of scattered about. I gotta sneeze. I don't know what this will do. If we get an invalid test case or a failed test case or what have you. I don't know, man. There's so many. I shouldn't say there's so many. There's. Oh, we got it. Okay, sweet. I wasn't really sure. I mean, I probably could have thought up this test case where it's kind of a degenerate case where you just kind of straight down, child after child. That was my fault. That was my mistake. I really could have thought of that. I should have missed that one. However, excuse me. Also, I think I get 100% with this, probably. It's only, yeah, there we go. There's only 1,000. The test case is really small. It's only 1,000 nodes. And then also the memory, if you do this iteratively as opposed to recursively, I think it's a lot easier to think about it recursively. Or it just seems to be a little bit easier to think about it recursively. But if you were to do this iteratively instead of recursively, you'd use a lot less memory, I think. You use significantly less memory. Each stack stores memory. Each recursive call creates another call stack. So okay, good, we still solved it. Alright, I mean it took 40 minutes. Not great, and we got it wrong, technically, or the first one was wrong. I missed something important here. The previous current values, keeping that state properly set up. Yeah, kind of unfortunate, I guess. Yeah, kind of unfortunate. There were a few errors here that kind of held me up. It's definitely, there were a few things I wanted to keep track of. I was manipulating this. There were a few errors. Yeah, it's tricky with linked lists. It's tricky. But, okay, we'll take it. Not bad. Alrighty. already, so I'll end there for this problem. So yeah, thanks for watching, and talk to you soon. Take care.